Hello and welcome back to Zig's Math Lessons. I'm your host, Ziggleby Stunk. Good to have you back. This is where we become the best math, science, technology, and engineering students for miles around. Let's take a look at the Binomial Theorem. What we're going to look at here is powers of a binomial. A binomial is two terms in a bracket, let's call it. A plus B. And when we raise that to some exponent, some integer exponent like 1, 2, 3, 0, 5, when n takes on different values, what does the expanded form look like? So I'm going to run n from 0 through 5 here. Now let's take a look at what the expanded form tends to look like. A plus b to the 0, we know that's the number 1. A plus b to the 1, we know that's 1a plus 1b. A plus b squared, well, when we square a binomial, we've been doing this for a while now, we know that we'd go first term squared, a times b times 2, so 2ab, and then b squared. If you were to take a plus b squared and multiply it again by a plus b, then you would have a plus b cubed. If you were to do that, and I suggest you do on a blank piece of paper, work it out and find out that yes, a plus b cubed really is this. It's 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. Similarly, a plus b to the fourth looks like this, and a plus b to the fifth looks like this. And hidden within here, we can see that the coefficients are from Pascal's triangle. Hidden in here is the triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 3 plus 3 is 6, 3 plus 1 is 4, 1. 1 plus 4 is this 5, 4 plus 6 is this 10, 6 plus 4 is this 10, and so on. The coefficients come from Pascal's triangle. That's why I laid them all out like this, just to show you that. Let's make some general observations about a plus b to the n. Here's the results. This is a plus b to the n, with n equals 0, 1, 2, up to 5. First of all, the degree of each term is n. Degree means the sum of the exponents on the variables. Consider this term. The sum of the exponents on the variables is 4 plus the 1 that's on the b. That makes 5, and we note that n is 5. Take a look at this term. Add up the exponents, 2 plus 2, 4, and we notice that that's equal to 4. N is 4. So the degree of each term is always n. This number here tells me the sum of the exponents on any term. 2 plus 3 is 5, and of course that's 5. That's interesting. Next, the number of terms is always n plus 1. This means that if this is a 3, for example, we would expect to see 4 terms, 3 plus 1. So we have 1, 2, 3, 4 terms, 3 plus 1 terms. There's a 5, I would expect to get 6 terms, 1, 2, 3, 4, 5, 6. You always get n plus 1 terms. That's another little pattern. Next, the coefficients are from the nth row of the triangle, the nth row. So we notice here that the coefficients in this row is 1, 5, 10, 10, 5, 1, and that is in fact the nth row, the fifth row of Pascal's triangle. And finally, there are 3 patterns to be found amongst the terms. These patterns look like this. First pattern we just did. The coefficients are from the nth row of Pascal's triangle. The second pattern looks like this. That's A. Observe A. We see A to the 5th, to the 4th, to the 3rd, to the 2, to the 1, to the 0. That's what I'm calling a pattern. Another pattern is, look at this, this is B, and if you look at the terms, B goes to the 0, to the 1, to the 2, to the 3, to the 4, to the 5. So A has its pattern, B has its pattern, and the coefficients have their pattern from Pascal's triangle. Let's use this knowledge to use the binomial theorem to expand and simplify a binomial power. Okay, there's a binomial power, and we notice that A is 3x squared, while B is 2, and n is 4. We'll simply expand this now using what we know. Solution: as n equals 4, gather the coefficients from the fourth row of Pascal's triangle. And the fourth row of Pascal's triangle is 1, 4, 6, 4, 1. Write it out yourself and confirm it. Write out the triangle and see that, yes, this is the fourth row of the triangle. I say gather the coefficients so that they're handy, because we're going to need them to write out the terms of this power. So I've got my coefficients handy. Next, apply the three patterns and simplify. Let's begin. Okay. The procedure is as follows. Reach up here and take the first coefficient, put it down here, like this. There it is, there's that 1. Take A, which is 3x squared, to the fourth. So I've started that pattern that goes a to the n, a to the n minus 1, and so on. So I've started. Notice the use of brackets. The brackets mean multiply. They're needed. Put a plus sign and reach up here. Grab the next coefficient, which is 4, and put it down here. Plus 4, in brackets, times. Now we'll take 3x squared to the 4, make it 3x squared to the 3, because we're starting our pattern that's going to go 4, 3, 2, 1. Meanwhile, 2 has started off at not there, 2 to the 0. It's become 2 to the 1, because it will become 2 to the 2, 2 to the 3, 2 to the 4, and so on. Next, reach up here and take a coefficient, which will be plus 6 in brackets, and then apply the rest of the patterns. 3x squared to the 4, 3x squared to the 3, now 3x squared to the 2. Meanwhile, 2 has been to the 0, to the 1, and now it's to the 2. And finally, well, not finally, but next, reach up here, grab a coefficient. The next coefficient is this 4, so it will be plus 4 times 3x squared to the 4, 3x squared to the 3, 3x squared to the 2. Now it's 3x squared to the 1. And let's look at the 2's. 2 to the 0, 2 to the 1, 2 to the 2. This is now 2 to the 3. All multiplied with brackets. Without the brackets, things can go wrong. So put brackets on them. And finally, reach up, take the last coefficient. So this will say plus 1 times, and 3x squared to the 1. Now it's 3x squared to the 0, so it's not there. Let's follow this 3x squared. 3x squared to the 4, 3x squared to the 3, 3x squared to the 2, 3x squared to the 1. Now 3x squared is gone. Meanwhile, 2 has gone. It's gone. 2 to the 1, 2 to the 2, 2 to the 3. It will be 2 to the 4. Now the process involves simplifying the terms. Now that we have the terms, we must simplify. Now 1 times can be ignored because everything's 1 times. And 3 to the 4th is 81x to the 8. So it will be 81x to the 8. This term here when simplified, 81x to the 8. Consider this one. 3 cubed is 27. 27 times 2 is 54. And 54 times 4 is 216. X to the 6, because in that configuration we multiply exponents. Next term. 2 is squared, that's 4. 3 is squared, that's 9. 9 times 4 is 36 times 6, again 216, because 9 times 4 is 36, and 36 times 6 is 216. x to the 4. Here, 2 to the 3 is 8, and 8 times 3 is 24, and 24 times 4 is 96. So it'll be 96 x squared. And finally, 2 to the 4 is 16 times 1. We won't mention that. So 2 to the 4 is just 16. Binomial theorem at work, creating for us this binomial expansion of this binomial right here. That is the result of raising that to the exponent 4. Next example for practice. Use the binomial theorem to expand and simplify the binomial power 2x minus y to the 5th. Note here, we've got a minus sign in the brackets. Okay, shouldn't be a problem. Solution. As n equals 5, gather the coefficients from the 5th row of Pascal's triangle. And if you wrote it out and went to the 5th row, you'd have 1, 5, 10, 10, 5, 1. Those are the coefficients. Next, apply the 3 patterns and simplify. Okay, 2x minus y to the 5th equals. Now, reach up, grab a coefficient. We'll use 1 times and then 2x in brackets to the 5th. That's our start. Next, reach up, take the next coefficient, which is 5. It will be 2x in brackets to the 4th times minus y to the 1. Reach up, take the next coefficient, which is 10, and then 2x to the 3rd times minus y squared. Notice how 3 plus 2 is 5. Next, reach up. We've done the first 10. We've got to reach up for the second 10. 10 times 2x to the square, or 2x to the 2, times minus y to the 3. Next, reach up for the next coefficient, which is 5. So it will say plus 5 times 2x to the 1 times minus y to the, now it's going to be 4. Notice the pattern. Minus y to the 0, minus y to the 1, minus y to the 2, minus y to the 3, now minus y to the 4. The coefficients, 1, 5, 10, 10, 5, and we're about to do the last one. And meanwhile, 2x to the 5, 2x to the 4, 2x to the 3, 2x to the 2, 2x to the 1, 2x will be gone. So on the end, 1, 10, 5, 1. The coefficient is 1, this last one from there. Minus y to the 5, because it went minus y to the 3, minus y to the 4, minus y to the 5. And 2x has now vanished, because it was 2x squared, 2x to the 1. It's 2x to the 0. So here we have our terms. There should be 6 of them, because n is 5. Let's count them. 1, 2, 3, 4, 5, 6 terms. Good. Now we have to simplify the terms. Looking at this one, 1 times we'll ignore. 2 to the 5th is 32, x to the 5. Next, it will be a negative term because we have a negative y times multiplying in. So this will be a negative term, and it will be 2 to the 4th, which is 16 times 5 is 80. So it will be negative 80 x to the 4y. Next, it will be a positive term because the negative y is squared, and negative things, when squared, become positive things. So this will be 2 to the 3 is 8 times 10, 80 again. It will be plus 80x cubed y squared. Next, it will be negative y cubed. Therefore, it's going to be a negative term because negative things, when cubed, become negative things. The reason being is that the exponent is odd. So we could say, let's see, 2 squared is 4 times 10 is 40, x squared y cubed with a minus sign. 40x squared because of this, y cubed because of this, negative because there's a minus sign here, and this is odd. Next, this is now even, So the negative sign will become positive. So this will be a positive term. It will be plus something. And 5 times 2 is 10, so it will be plus 10xy to the 4th. And lastly, 1 times can be ignored. It will be negative because of the odd 5 here. And so it will be minus y to the 5th. And now this is the expansion of this. I'm Ziggleby at Bishtuk. Thanks for watching. If you liked it, leave a like. If you like the content, please subscribe. Check back later for updates and new videos for the next unit, and I'll see you soon.